In non-rechargeable cells, reactions go to completion and cell reactions cannot be reversed. The flow of electrons between half cells provides the current required for the battery-powered device to work. There are many different versions of non-rechargeable cells, but they all work on the same principles. You don't need to know the exact chemical used in your exam, but you need to understand the role of all the components. So here we have an example of a non-rechargeable cell, which is a zinc manganese 4 oxide cell. In terms of its setup, you have a carbon rod, which is acting as an unreactive, inert positive electrode that allows electrons to flow. You have a non-reactive porous separator, which acts as a salt bridge. And as we know, salt bridges allow ions to pass through. The walls of this cell are made of zinc, and in this case, they act as the negative electrode. And because it's the negative electrode, they'll be attracting positive ions. The oxidation reaction occurs here, so the zinc solid loses electrons. And because that solid zinc is reacting, the cell will eventually leak if used for a long time. Inside the walls, you have a zinc chloride paste, which provides the important Zn2+ ions required for the half cell. And then the manganese oxide paste is where the reduction reaction occurs, so you'll see the addition of electrons. And here are two reduction half equations. So now let's write the overall equation. So because this is the more positive E theta value, remember that means that reduction is going to take place. So we keep that equation running left to right. The more negative E theta value is our oxidation reaction, so we know we're going to need to reverse that equation in order to show the loss of electrons. So I'll do that right now. Let's balance these electrons. I need to multiply this equation by 2 before adding them together. So overall, then I'm going to remove those electrons to give my overall equation. And then the overall EMF. So take the more positive EMF, take away the less positive EMF, so in effect we're adding them to get a final EMF of 1.50 volts. Now in a rechargeable cell, the reactions can be reversed by passing an electric current through the circuit. This forces electrons to flow from the positive electrode to the negative electrode. Rechargeable cells are more environmentally friendly than non-rechargeable, obviously because the metals and their compounds are reused. Rechargeable cells can also be responsible, however, for the release of CO2 into the atmosphere, as the electricity used for recharging the cell may come from power stations which have been burning fossil fuels. So there's really no perfect solution here. Let's look at an example of a rechargeable cell, the lead acid battery. So the equation when discharging, so in effect when it's acting as a battery, is as follows. You have your oxidation reaction, which remember occurs at the negative electrode, the cathode. You've got your solid lead reacting with aqueous sulfate ions, forming lead sulfate. There's our loss of electrons, as you'd expect with an oxidation reaction. Your reduction reaction now, which occurs at the positive electrode, the anode. Lead oxide reacting with hydrogen ions, which remember have been donated by the acid. There's reduction taking place with the addition of 2 electrons. So what is our overall equation? Well, look, the electrons balance, which means we can just add the 2 equations together. Now, when the current is applied to the battery so that it's recharging, the reactions here will reverse. So I'll write those 2 equations occurring now at the negative and positive electrode together with the new overall equation. Again, the electrons cancel out, so the overall equation is how about a lithium-ion battery now? So the first set of equation when the lithium ion battery is working as a battery, so when it's discharging, there's the loss of electrons. What about the reduction reaction, which occurs at the positive electrode? The overall reaction, thankfully the electrons are already balanced. Now when a current is applied, so we know that the battery is recharging, as you'd expect the reactions reverse. So at the negative electrode, let's reverse that reaction and make it reduction. At the positive electrode, let's make it oxidation. And then the last example I want to show you is the nickel-cadmium battery. So when discharging, when it's acting as a battery, the oxidation reaction which occurs at the negative electrode is as follows. The reduction reaction occurring at the positive electrode is as follows. You'll need to multiply this equation by 2 in order to be able to cancel out the electrons to give the overall reaction of this. And then as we know, when a current is applied to the battery and it's recharging, the reactions reverse as follows. Again, we've multiplied this equation by 2 in order to cancel out the electrons to provide this as our overall reaction. Hydrogen-oxygen fuel cells. So hydrogen-oxygen fuel cells are used to generate electricity without producing carbon dioxide. So they're thought to be a more green approach to releasing the energy we need to power our homes. The hydrogen-oxygen fuel cell does not need to be electrically recharged, and the reason for that is because the reactants are continuously supplied to the fuel cell. We find that they're more efficient than internal, more traditional combustion engines, and that's because a greater proportion of the energy available from the hydrogen-oxygen reaction is converted into useful energy. The major hazard, though, associated with the use of these fuel cells is the fact that hydrogen is extremely explosive, and we can't say that they're entirely carbon neutral, despite the fact they don't release carbon dioxide. And that's because the hydrogen used in them is often produced from crude oil or via electrolysis. Now here's the setup of an alkaline hydrogen-oxygen fuel cell. You've got your electrodes. They'll be made from platinum, which is an unreactive inert metal. They're porous in order to increase the surface area, and that's important because after all, platinum is extremely valuable and inexpensive. You have a non-reactive semi-permeable membrane, which is your salt bridge, allowing the hydroxide ions to pass through. As aforementioned, it's an alkaline fuel cell, meaning that the electrolyte being used is sodium hydroxide. If you were using an acidic fuel cell, it would have a strong acid, such as phosphoric acid. The current is generated because electrons are produced by the hydrogen electrode and are accepted by the oxygen electrode. So here's our 2 reduction half equations. As I've already mentioned, it's the reactions for the alkaline fuel cells due to the presence of the hydroxide ions. If you're asked about an acidic fuel cell, you'll need to use the half equations which contain H+ ions rather than the hydroxide ions. So looking more closely at the redox reactions taking place, the oxidation reactions where electrons are lost, this will occur at the negative electrode. Your reduction reaction where electrons are gained occur at the positive electrode. And then, as you can see, the electrons balance out, so it's possible to combine both equations to form the overall equation. And as you can see, it's such a clean source of energy because you have hydrogen reacting with oxygen, producing water with no carbon dioxide formed. Then the overall EMF, here's our E theta cell. We're doing E theta reduction minus oxidation, or the more positive E theta value minus the more negative E theta value to give an overall EMF of plus 1.23 volts. Now the value is the same for both the alkaline and acidic hydrogen fuel cells because the overall reaction is the same. Question 2. This question is about the development of lithium cells. The value of E theta for lithium suggests that a lithium cell could have a large EMF. The table below shows some electrode potential data. Use data in the table above to explain why an aqueous electrolyte is not used for a lithium cell. So we need to look at the E theta values here, and we can see that the E theta value for the lithium is more negative than that for water, hence the mention of the aqueous electrolyte. And therefore what that means is the water will oxidize the lithium to Li+, basically meaning that lithium would react with the electrolyte. Obviously, we really don't want that lithium reacting with water. In the 1970s, lithium iodine cells became a common power source for heart pacemakers. Lithium iodide is the final product of the cell reaction. Use the data in the table above to calculate the cell EMF of a standard lithium iodine cell. We're looking at these two values. So to find the E theta value of the cell, we do our reduction reaction, the one with the more positive E theta value, minus the oxidation reaction to get 3.58 volts as our final answer. An EMF value for commercial lithium iodine cell is 2.8 volts. Suggests why this value is different from the value calculated in part B. It's most likely due to the presence of non-standard conditions. In some lithium cells, lithium perchlorate is used as the electrolyte to reduce the oxidation state of chlorine. So oxygen is -2, lithium is +1. Overall, we know that oxygen is producing -8, so that means that chlorine must be +7 in order to make it neutral. In other lithium cells, lithium cobalt oxide electrodes and lithium electrodes are used. Give an equation for the reaction that occurs at the positive lithium cobalt oxide electrode. This is what I was just going through. You do need to learn these off by heart. Give an equation that occurs at the negative lithium electrode. Remember, the way round we're writing these equations is based on the battery in operation, so discharging. So that's why this lithium equation is the oxidation reaction. Fuel cells are an increasingly important energy source for vehicles. Standard electrode potentials are used in understanding some familiar chemical reactions, including those in fuel cells. A salt bridge was used in a cell to measure electrode potential. Explain the function of the salt bridge. Allows ions to move. Completes the circuit. Use data from the table to deduce the halide ion that is the weakest reducing agent. So it's oxidized. We need the one which is least likely to be oxidized, so the one with the highest E theta value. Let's look at all these values. Because it's being oxidized, remember we need to look at the right-hand side, so that's why it's the fluoride ion, which makes sense, it's a halide. Use data from the table to justify why sulfate ions should not be capable of oxidizing bromide ions. The bromide ions are being oxidized, which means they need a more negative E theta value compared with what's going on with the sulfate ions. So we're looking at these numbers here, and sure enough, the bromide equation has a higher E theta value. So that's what I'm saying there. The E theta value of the bromide equation is greater than that of the sulfate equation. Use data from the table to calculate a value for the EMF of the hydrogen-oxygen fuel cell operating under alkaline conditions. So remember from what I just taught you, to find the overall EMF, we take this equation here, which represents reduction. This equation here represents oxidation, and therefore EMF is our reduction minus the oxidation, which gives us a value of 1.23 volts. There are two ways to use hydrogen as fuel for cars. One way is in a fuel cell to power an electric motor. The other is as a fuel in an internal combustion engine. Suggests the major advantage of using the fuel cell. Remember, I said that a fuel cell converts more of the available energy from combustion of hydrogen into useful energy in the car.